The remedial technology we used was cement-based stabilization solidification of the lead-contaminated soils. The off-site disposal of that much material would cost approximately $600,000. The on-site disposal of that material cost only $100,000. In addition, we also had a savings in backfill and the use of processed gravel as a binder for the parking lot, which resulted in another $30,000 of savings.
The most familiar use of Portland cement is as the key ingredient in concrete used to build our roads, bridges, and buildings. Portland cement, this fine gray powder, has found additional use in the treatment of hazardous waste and the cleanup of contaminated land. Solidification stabilization involves mixing Portland cement into contaminated material to physically solidify and chemically stabilize the contaminants within the treated material. Solidification stabilization has been successfully used to treat contaminated material at an increasing number of sites, including those involved in urban revitalization or brownfields redevelopment. At this brownfield site in Boston, solidification stabilization was used to treat lead and petroleum contaminated soils. The treatment produced material that was reused at the site as pavement base for a parking lot.
This is the oldest electric generating station for the MBTA in Boston. The site is now in the process of being gutted and renovated for its motif. This area of town is all considered brownfield, so all the renovation work that's being done is coming under various incentives to revitalize the inner city. Our participation is involved in taking the hazardous leaching lead soils on this site and the petroleum contaminated soils on the site and incorporating it with stabilizers, specifically Portland cement for the hazardous levels of leaching lead. The material here is a backfill that was brought in when they put the tankage in the ground for the underground storage tanks. The lead contamination is a product of the fly ash that came out of the generating station over the years, a very, very heavy deposit and substantial levels of leaching lead and high levels of total lead.
Cement-based solidification stabilization was first used in the U.S. during the 1950s to treat radioactive waste from weapons development and manufacture and nuclear power generating facilities. This technology continues to be used today to treat a wide variety of wastes and contaminants. The U.S. Environmental Protection Agency considers solidification stabilization to be an established treatment technology. This technology has been used at 25% of Superfund sites where sources of contamination have been addressed.
Cement-based solidification stabilization can treat soil, sediment, and sludge for a wide range of inorganic and organic hazardous constituents.
Solidification stabilization is also used to treat hazardous wastes generated by industry. The U.S. Environmental Protection Agency considers solidification stabilization as best demonstrated available technology for over 50 RCRA-listed hazardous wastes. Solidification and stabilization are used to describe the effects of this treatment. In untreated soil with contaminants, groundwater and surface water move through the contaminated soil, dissolving and physically carrying away contaminants. During solidification treatment, cement mixed into soil reacts with water, or hydrates. This reaction forms physical bonds that encapsulate and immobilize contaminants. Solidification often lowers the permeability of the treated material. This inhibits water movement and prevents leaching. Stabilization describes chemical changes to the hazardous constituents. Cement added to the contaminated soil begins to hydrate, producing calcium hydroxide. This increases the pH of the material. Calcium hydroxide in the pore water reacts with some of the contaminants, converting them to a less soluble compound. Reactions involving cement and water also produce carbonate and silicate compounds. Some contaminants present in the waste become incorporated into these compounds, forming insoluble carbonate and silicate compounds. This further reduces the leachability of the contaminants.
Solidification stabilization treatment can also reduce toxicity of some heavy metals through the use of additives and mixing techniques that can change the metal's valence state. Portland cement has many advantages over other binding reagents.
First of all, it's manufactured to standards set by the American Society for Testing and Materials. Quality control ensures a uniform product and predictable performance.
Cement is a generic product. It is produced at over 125 plants in the U.S. and Canada, and it can be purchased in bags or in bulk. Often, less cement is needed to create the desired treatment results than other reagents. Determining the right amount of Portland cement to mix with contaminated material begins with laboratory work. Treatability testing usually involves testing various mix designs for physical and chemical changes to the treated material. Tests should be selected based on the anticipated reuse or disposal conditions for the treated material. Physical testing usually includes measuring the treated waste's ability to support vertical loads. This testing may be required by the EPA to prove that free liquids are actually chemically bound instead of merely absorbed. A gain in strength indicates chemical binding of free water. Typically, at least 50 psi unconfined compressive strength is required. Hydraulic conductivity tests are sometimes required to measure the rate at which a liquid will pass through treated material. Chemical test procedures are typically required to determine the leachability of hazardous constituents from the treated material. At the project site, cement can be mixed into the contaminated material using a variety of methods. The Brownfields Redevelopment Project in Boston used ex situ mixing and treatment. Contaminated material was excavated and processed through a mobile treatment plant.
On this particular site, they're going to reuse it as a paving base because we're going to give structural integrity to the product by using the cement, and they'll be able to use it as a paving base, saving themselves thousands of dollars.
Contaminated soil is first run through a screening process to separate oversized material. Screened material is conveyed to the pug mill hopper. Inside the pug mill, twin rotating shafts with paddles mix the contaminated soil with Portland cement.
What we're doing today is we're adding Portland cement into it to hydrate the product and give stability and take the TCLP levels of the lead down below a non-detect.
Computer controls on the pug mill assure that the proper amount of cement is added to the soil. Treated soil exits the pug mill and is staged for reuse as pavement base.
Another mixing method uses an in situ blender to mix cement into previously excavated material. Dry cement, or a mixture of cement and water, is jetted into the material while a rotating drum with cutting teeth mixes the cement with the contaminated material. In situ or in-place mixing can also be carried out by using a large rotating auger. This equipment drills into contaminated material while injecting a cement grout. Another mixing method uses a conventional road reclaimer. Cement is spread in front of the machine.
A rotating set of tines aggressively mixes the cement into the contaminated soil, treating to a depth of up to 2 feet. Additional layers of material can be placed on top of previously processed material and treated.
Portland cement-based solidification stabilization is a versatile and effective treatment technology. It's an established and widely used solution for cleaning up contaminated sites. It can treat soil, sediment, and sludge for a wide variety of organic and inorganic contaminants. Cement-based solidification stabilization can safely treat contaminated material and turn an economic liability into an economic asset.
The Portland Cement Association has published additional technical information on the use of solidification stabilization treatment technology.
Contact us for additional information or with any specific questions you may have. Thanks for watching.